Hello, in this lecture we'll find out the length of line segment X using two different methods. In the drawing we have a semicircle inside a quarter circle, and we know that side AO equals to 6 units, side AC is tangent to the semicircle at this point, and we want to find out the length of side AC that is equal to X. So we'll start with the first method, and we'll define the center of the semicircle as point P, and we'll define the point of tangency of tangent AC with the semicircle as D. Actually, because of the fact that this is a quarter circle, it means that point O is the center of the quarter circle, and this angle equals to 90 degrees. And so point O is the center of the quarter circle, and point A is a point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, the radius AO is the radius of the quarter circle that is equal to 6 units according to what is given us in the question. And here OB, it is also the radius of the quarter circle because of the fact that it starts from the center of the quarter circle, that is to say from point O, and ends at point B, that is a point on the quarter circle itself. So it is the radius of the quarter circle that is equal to 6 units. But OB, line segment OB, it is not only the radius of the quarter circle, but it is also the diameter of the semicircle. Okay, OB is the diameter of the semicircle, and we know that the diameter of the semicircle equals to 6 units. If the diameter equals to 6 units, it means that the radius will be equal to half of it, that is 6 over 2. That is to say, the radius of the semicircle equals to 3 units. So here OP is 3 units, and PB is also 3 units. And if we join points P and D together by a straight line, PD is also the radius of the semicircle that is equal to 3 units. All those 3 line segments, they are defined as the radii of the semicircle. Why? Because they start from the center of the semicircle and end at any point on the semicircle itself, and this is exactly the definition of a radius. Okay. The next step, we join points A and P together by a straight line. And I will present to you a new rule that is actually rule number 1. According to rule number 1, the length of two tangents from a common external point to a circle are equal. I write it down. So I'll read rule number 1 again. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we also have point P, here, this is point P, that is defined as an external point of this circle. Why point P is an external point of this circle? Because of the fact that point P is not located inside this circle, nor on this circle, but it is located outside of this circle. For that reason, it is defined as an external point of this circle. So if from the external point P, we will draw two tangents to this circle. So here, the first tangent this is the first tangent, and we will define the point of tangency of the first tangent with this circle as point A, and we will also draw another tangent to this circle, this is the second tangent to this circle, and we'll define the point of tendency of the second tangent with this circle as point B. And according to rule number 1, the lengths of two tangents, that is to say the first tangent is PA, the length of the first tangent is PA, and the length of the second tangent is PB. And according to rule number 1, the lengths of two tangents from a common external point, the common external point is point P, to a circle, to points A and B are equal. That is to say, PA is equal to PB. Because the length of the first tangent is PA, the length of the second tangent is PB, and according to rule number 1, those lengths are equal to each other. That is to say, PA equals to PB according to rule number 1. So whenever you draw two tangents to a circle from a common external point of that circle, like in this drawing, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. So we actually can implement rule number 1 in our drawing, because in our drawing we have the common external point, point A, and from this common external point, point A, we have two tangents to this semicircle. The first tangent is tangent AO. Tangent AO is tangent to the semicircle at point O. And the second tangent is tangent AD. Tangent AD is tangent to this semicircle as point D. And according to rule number 1, the verbs of those two tangents are equal to each other. That is to say, AO equals to AD according to rule number 1. Okay, so I write it down. I repeat again, AO equals to AD according to rule number 1. Okay? But according to what is given us in the question, AO equals to 6 units. Okay? So I can write here that AO equals to 6 units. And for this equation, 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. AD is also equals to 6 units. So I can write here that line segment AD equals to 6 units. In the next step, we will prove that those two right angles can go into each other according to side rule. So we'll prove that the right green triangle AOP will go into the right green triangle APD according to side rule. So I write it down. We prove that the right triangle APO, this right green triangle, can go into the right green triangle APD this is the sign of congruent, and they congruent to each other according to side rule. Okay? So, first of all, side AO equals to side AD, they are both equal to 6 units according to rule number 1. AO equals to AD, and they are both equal to 6 units according to rule number 1. In addition, side AP equals to itself. Side AP is the common side that belongs to both triangles. So AP equals to AP. It's the common side that belongs to both triangles. And finally, side OP equals to side PD equals to 3 units. It is the radius of the semicircle. equals to PD equals to 3 units. So we actually proved that all the sides of triangle APD convert to all the sides of triangle APO. Therefore, those two triangles convert to each other according to side rule. And from the fact that those two triangles convert to each other, we will derive that those two angles, they are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two great triangles congruent to each other, therefore those two corresponding angles will be also equal to each other. So angle OAP equals this angle equals to angle PAD, this angle, according to the rule that corresponding angles in congruent triangles are equal to each other. So angle OAP equals to angle PAD. If we define angle OAP as theta, so here angle OAP equals to theta according to our definition. Then from this equation theta equals to angle OAP equals to angle PAD, we will derive that angle PAD is also equals to theta. Okay, so this angle is also equals to theta. So both those two angles are equal to theta. In the next step, we'll focus on triangle AOP, this triangle, the right triangle, triangle AOP. In the right triangle, triangle AOP, we know that times theta equals to OP over OA. I will repeat again. In the right triangle, triangle AOP, times theta equals to OP over OA. OP equals to 3 units, it is the radius of the semicircle, and OA equals to 6 units according to what is given as the question. So times theta equals to 3 over 6. We divide both the numerator and the denominator of this side of the equation by 3. And we get that 3 over 3 is 1 and 6 over 3 is 2. So in conclusion, we found out that times theta equals to 1 half. Times theta equals to 1 half. Okay, times theta equals to 1 half. In the next step, we will join points O and C together by a straight line. So, we actually created here triangle AOC. This is triangle AOC. So in the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle AOC. So what is the law of cosines? I've already mentioned it in the previous lecture. The law of cosines is true in any triangle. So if we have triangle ABC, that could be any triangle. This is triangle ABC. And we know that side AB of triangle ABC equals to A units in its length. Side AC of triangle ABC equals to B units in its length. And side BC equals to C units. And the angle between side AB and side AC is alpha. Then, according to the law of cosines, we'll get that C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. Okay? I'll repeat again. In this triangle, triangle ABC, according to the law of cosines, C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. And as I've already said, you can implement the law of cosines in triangle AOC. So I'll copy triangle AOC in this page and we will implement the law of cosines in triangle AOC. Okay, so side AO equals to 6 units, and AC is the line segment that we are looking for, that is equal to x according to what is given us in the question. What is the length of side OC? The length of side OC is, we know that point O is the center of the quarter circle. Point C is the point on the quarter circle itself. And this is exactly the definition of a radius. That is to say, OC is the radius of the quarter circle that is equal to 6 units. So OC equals to 6 units. So this is triangle AOC that I copied from the original drawing. We know that angle OAC equals to theta plus theta, that is 2 theta. Side AO equals to 6 units, side OC equals to x, and side OC equals to 6, and side AC equals to x. So we'll implement the Pythagoras theorem on this triangle, triangle AOC. This is triangle AOC. And according to the Pythagoras theorem, this will be equation number 1. OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. I repeat again, OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. Okay? So here, according to equation number 1, OC squared. OC equals to 6 units. Therefore, OC squared is 6 squared, that is 36. That is equal to AO squared. AO is also equals to 6 units. Therefore, AO squared is 6 squared, that is 36. Plus AC squared. AC equals to X, according to what is given as the question. So AC squared will be equal to X squared minus 2 times AO is 6 times AC is X times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled. So what is left from equation number 1 after we cancel 36? In this side of equation number 1 we have 0, that is equals to x squared, minus 2 times 6 is minus 12. So this expression in total it is equals to minus 12 x times cosine 2 theta. So here we will add 12x cosine 2 theta to this equation, equation number 1, and we will get that according to equation number 1, (12x cosine 2 theta equals to x squared. I'll repeat again. According to equation number 1, we found out that 12x cosine 2 theta equals to x squared. Here we will divide this equation, equation number 1, by x. I must emphasize the fact that the reason that we can divide equation number 1 by x is because of the fact that x is the length of side AC. That is to say, it must be x as a length must be a positive number. It can never be equal to 0. Therefore, it is allowable to divide equation number 1 by x. Okay. So here x will get cancelled and we left only with 12 times cosine 2 theta, that is equals to x squared over x is x. So in conclusion, according to equation number 1, we found out that 12 times cosine 2 theta equals to x. So the only thing that is left to do in order to find out the value of x, that is the line segment that we are looking for, is to find out the value of cosine 2 theta. Okay? But actually we have trigonometric identity for cosine 2 theta. Actually, cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. Okay, the trigonometric identity for cosine 2 theta is that cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. But we have already found out that tangent theta equals to 1 half. I'll repeat again. We have already found out that tangent theta equals to 1 half. So we can substitute tangent theta in this trigonometric identity by 1 half. We'll do it now and we'll get that cosine 2 theta equals to 1 minus tangent square theta. If tangent theta equals to 1 half, it means that tangent square theta will be equal to 1 half squared. Okay, so in the numerator we have 1 minus 1 half squared over 1 plus tangent square theta is 1 half squared. In conclusion, I found out that cosine 2 theta equals to 1 minus 1 half squared over 1 plus 1 half squared. 1 half squared is 1 quarter. So, here we write down that cosine 2 theta equals to 1 minus 1 quarter over 1 plus 1 half square is 1 quarter. One minus 1 quarter is 3 quarters, while 1 plus 1 quarter is 5 quarters. And here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. In conclusion, we actually found out that cosine 2 theta equals to 3 over 5, that is 3/5. Cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in this equation, equation number 1, by 3/5. So according to equation number 1, 12 times cosine 2 theta equals to x. We'll substitute cosine 2 theta by 3/5 and we'll get that 12 times cosine 2 theta is 3/5 equals to x. So actually x equals to, according to equation number 1, x equals to 12 times 3 is 36 over 5. 36 over 5 is 7.2 units. So we found out that x, the line segment that we are looking for, that is also equals to AC, it is equals to 7.2 units. Okay. Here x that is equal to AC also, it is equal to 7.2 units. We finished with the first method. In the next step, I will present to you how to find out the length of line segment X that is also equal to AC according to the second method. Okay. In the second method, we will use in all the things that we have already found out in the first method. So here, the center of the semicircle is at point P. The point of tendency of tangent AC with this semicircle is at point D. We have already found out that this is a right angle. Point O is the center of the quarter circle. OP is 3 units, PB is also 3 units, and PD is also equal to 3 units. All the line segments here are the radii of the semicircle that is equal to 3 units. We join points A and P together by a straight line. In the first method also, and we actually proved that those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other according to side rule, we concluded that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle equals to theta, then the other angle must be also equal to theta, because those two angles are equal to each other. So we did all those things in the first method, so I'll not repeat on it. In the second method, we will do another construction that we haven't done in the first method. We will extend line segment AC and line segment OB by a straight line until they intersect with each other. And we will define the intersection point between the extended line segment AC and the extended line segment OB as E. So actually, by doing this construction, we created here triangle AOE that is a right triangle. Okay. This is triangle AOE, and in this triangle AOE, AP, line segment AP, divides angle OAE, this angle, into two halves. Each half equals to theta. That is to say, this is exactly the definition of angle bisector. That is to say, AP is angle bisector of angle OAE. Why? Because it divides it into two halves. Each half equals to theta. And because of the fact that AP is angle bisector, we will implement the angle bisector theorem in this triangle AOE, but first of all, I will present to you what is exactly angle bisector theorem, and only after that we will implement the angle bisector theorem in this triangle, triangle AOE. So what is angle bisector theorem? Angle bisector theorem is true in any triangle angle bisector theorem So if we have triangle ABC, that could be any triangle, this is triangle ABC, and here line segment AD is angle bisector of angle BAC. So AD is angle bisector of angle BAC. Okay, I'll write it down. AD is angle bisector of angle BAC. Okay, so according to angle bisector theorem, so I write it here that AD is the angle bisector it is angle bisector of angle BAC. It divides it into two halves, each half equals to theta. So according to angle bisector theorem, the angle bisector in a triangle so we are relating to AD. AD is the angle bisector, so I write it here. This is AD in brackets in triangle. In this case we are talking about triangle ABC. Divides the side that it is. As you can see from the drawing, angle bisector AD is side BC. So we are relating to side BC. Actually, as you can see, angle bisector AD is side BC and divides it into two parts. The first part is part BD, the second part is part DC. And the ratio between those two parts is BD over DC. So the angle bisector AD triangle ABC divides the side that it is, that is BC, in a ratio that ratio is equal to BD over DC. So I write it down in the brackets. And that ratio is equal to the ratio between the angle legs. And here we are relating to the angle that has been bisected into two halves, that is to say angle BAC. Angle BAC, this angle BAC has two legs. The first leg is AB and the second leg is AC. And the ratio between those two legs is AB over AC. So that ratio, that is AB over AC, equals to the ratio that angle bisector AD divides side BC. That is actually BD over DC. Okay, I repeat again. The ratio that angle bisector AD divides side BC is BD over DC, and that ratio equals to the ratio between the angles legs. We are talking about angle BAC that has been divided into two halves. The legs of angle BAC are AB and AC, and the ratio between those two legs is AB over AC, and that ratio equals to the ratio that angle bisector AD divides side BC. That is actually BD over DC. So in conclusion, according to angle bisector theorem, in this right triangle ABC, that AD is angle bisector, AB over AC equals to BD over DC. Okay, this is actually the angle bisector theorem. Now we will implement the angle bisector theorem in our triangle, the right triangle AOE. So we copy the right triangle AOE in a new page, and we will implement the angle bisector theorem in the right triangle AOE. This right triangle AOE. In the right triangle AOE, AP is the angle bisector of angle OAE. It divides angle OAE into two halves. Each half equals to theta. So this is the right triangle AOE that I copied from the original drawing. And here AP is the angle bisector of angle OAE. So actually, according to angle bisector theorem, the angle bisector AP divides the side that it eats. Angle bisector AP each side OE. It divides this into two parts. The first part is OP and the second part is PE. And the ratio between those two parts is OP. The ratio between those two parts is OP over PE. And that ratio is equal to the ratio between the angle's legs. We are talking about the angle that has been bisected into two halves, that is to say angle OAE. Angle OAE has two legs. The first leg is AO and the second leg is AE, and the ratio between those two legs is AO over AE. Okay? Again, the ratio of that angle bisector AP divided side OE is OP over PE, and that ratio equals to the ratio between the angle's legs. We are relating to angle OAE, and the ratio between the angle's legs is AO over AE. So in conclusion, according to angle bisector theorem, the right angle AOE, we will get that OP over PE equals to AO over AE. Okay? Here, OP is the radius of the semicircle, that is to say it is equal to 3 units. So it is 3 over PE. That is equal to AO. AO is 6 units according to what is given as the question, over AE. So, in conclusion, we found out that according to equation number 1, 3 over PE equals to 6 over AE. We divide this equation by 3, and we will multiply it by AE, and we will get that according to equation number 1, 6 over 3 equals to AE over PE. Six over 3 is 2. So write it down. Here 2 equals to AE over PE. Here we will multiply this equation number 1 by PE, and we will get that according to equation number 1, 2 times PE equals to AE. So here, according to equation number 1, AE is twice as long as PE. So we will define PE as A. Here, PE equals to A according to our definition. So we can write here that P equals to A. And then in the original drawing also, PE equals to A according to our definition. Now we can substitute PE in equation number 1 by A. We'll do it now, we will get that AE equals to 2 times PE, and PE is A, so AE equals to 2 times A. A equals to 2 times A. Here, line segment AE equals to 2A according to equation number 1. P equals to A according to our definition. In the next step, we will implement the Pythagoras theorem on the same right triangle, triangle AOE. Okay? So I copy the right triangle AOE in a new page and we implement the Pythagoras theorem on this triangle AOE. You can see from the drawing that side OE equals to OP, that is 3 units, plus PE, that is A. So side OE equals to 3 plus A. Yeah. Side OE equals to 3 plus A. And we have already found out that side AE, the hypotenuse equals to 2A. So in the right triangle AOE, by PT is abbreviation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This will be question number 2. According to question number 2, the square of the hypotenuse is AE square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AO square plus OE square. AE equals to 2A, so AE square is 2A square. And it is equal to AO square. AO equals to 6, so AO square is 6 squared, that is 36, plus OE square. OE equals to 3 plus A, so OE square will be equal to 3 plus A square. So here we will open the brackets on both sides of this equation number 2, and we will get that according to equation number 2, two A squared is 4A squared, that is equal to 36, plus 3 plus A squared is 3 squared, that is 9, plus A squared, plus 6A. Thirty-six plus 9 is 45, so I'll write it down. Here 4A squared equals to 45, plus A squared, plus 6A. Here we'll subtract A squared from this equation number 2. And we'll get that according to equation number 2, 4A squared minus A squared is 3A squared. That is equal to 45. A squared minus A squared is 0, plus 6A. So here we'll divide this equation number 2 by 3, and we get that according to equation number 2, 3A squared over 3 is A squared. that is equal to 45 over 3 is 15, and 6a over 2 is 3a. So here we'll subtract 15 and also 3a. Here 6a over 3 is 2a. Here we'll subtract 15 and also 2a from this equation number 2, and we'll get that according to equation number 2, a squared minus 2a minus 15 equals to 0. So we have here a quadratic equation. The variable that we are looking for in this quadratic equation is a. So x equals to a. The coefficient a in this quadratic equation is 1. The coefficient b in this quadratic equation is minus 2. And the coefficient c in this quadratic equation is minus 15. Okay? And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So we'll put the data inside this formula in order to find out the value of the values of a, because here x equals to a. So x equals to a, so we substitute x by a, and we get that a equals to minus b, b equals to minus 2, so minus b is minus 2, that is plus 2, plus minus square root of b squared, b equals to 2, so b squared is minus 2 squared, that is 4, minus 4 times a is 1, and c is minus 15. So it is times minus 15 over 2a. A is 1, so 2 times 1 is 2. So a equals to 2 plus minus, here minus 4 times minus 15 is plus 60, and 60 plus 4 is 64. So inside the root, what is left is only 64 over 2. So here a equals to 2 plus minus, the square root of 64 is 8 over 2. So here we will have two solutions that are possible for a. The first solution for a is that a equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that according to the first solution, a equals to minus 3. That is a negative number. But here, a is the length of side PE of triangle APE. A is a length. So a is a length. And as a length, it must be a positive number. Therefore, it can never be equal to minus 3. It is a negative number, so we cancel this solution. And only the second solution is left. That is actually a equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that a equals to 5 units. A equals to 5 units. So we can write down here that a equals to 5 units. If a equals to 5 units, then 2a is 2 times 5, that is 10. That is to say, AE that is equal to 2a equals to 10 units, and PE that is equal to A is 5 units. In the next step, we'll find out the length of side BE. From the drawing, it is very easy to see that the length of side BE or of line segment BE equals to PE minus PB. PE minus PB equals to BE. I'll repeat again. From the drawing, it is very easy to see that B equals to PE minus PB. Okay. So BE equals to PE equals to A, that is 5 units, minus PB equals to 3 units, it is the radius of the semicircle. So in conclusion, we found out that BE equals to 5 minus 3, that is 2. We found out that BE equals to 2 units. So we can write here that BE equals to 2 units. In the next step, we will find out the length of line segment CE. What is the length of line segment CE? Here, from the drawing, it is very easy to see that the length of line segment CE, it is equals to AE minus AC again. AE minus AC equals to CE. I repeat again. CE equals to AE minus AC. So CE equals to AE. We have already found out that AE equals to 10 units. And AC is the line segment that we are looking for. And it is equal to X according to what is given us the question. So in conclusion, we found out that CE equals to 10 minus X. Here, CE equals to 10 minus X. In the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and then we will extend line segment VO by a straight line until it touches the circle. And we will define the touching point of the extended line segment VO and the circle as point M. So what is the length of line segment MO? O is the center of the quarter circle, that is also the center of the circle itself. M is the point on the circle itself, and this is exactly the definition of a radius. That is to say, OM is the radius of the circle, that is also the radius of the quarter circle that is equal to 6 units. So in conclusion, MO equals to 6 units because it is the radius of the quarter circle that is also the radius of the circle itself. Okay? So in the next step I will present to you a new rule that is actually rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, if two chords intersect with each other outside the circle, then the following equation is true. So, first of all, we have the external point P. Point P is the intersection point between the two chords. So the first chord is chord AB. This is chord AB. That intersects with chord CD. This is chord CD. So here you can see, as you can see from the drawing, chord AB intersects with chord CD at point P. So point P is the intersection point of chord AB with chord CD. Okay, so if this is the data that has been given to us, then the following equation is true, that PA times PB is equal to PC times PD. Okay, so I repeat on rule number 3 again. If two chords intersect with each other outside the circle, then the following equation is true, that PA times PB equals to PC times PD. So here we have chord AB that intersects with chord CD at point P. Point P is the intersection point of chord AB with chord CD. Then according to rule number 3, PA times PB equals to PC times PD again. PA times PB equals to PC times PD. So whenever you have two chords that intersect with each other outside the circle, then this equation is true. Okay, PA times PB equals to PC times PD. So we can implement rule number 3 in our drawing, because in our drawing we have chord AC intersects with chord MB at point E. Point E is the intersection point of chord AC with chord MB. This is actually, of course, outside the circle. Okay, so I write it down. In our specific drawing, we have chord AC intersects with chord MB. I'll repeat again, chord AC intersects with chord MB at point E. Point E is the intersection point of those two chords. I'll repeat again. In our specific drawing, we have chord AC that intersects with chord MB at point E. Point E is the intersection point of those two chords, and it is located outside the circle. Therefore, we can implement rule number 3. Therefore, according to rule number 3, we will get that EC times EA equals to EB times EM. I repeat again. EC times EA equals to EB times EM according to rule number 3. Because of the fact that chord AC intersects with chord MB at point E, then according to rule number 3, EC times EA equals to EB times EM. I repeat again, chord AC intersects with chord MB at point E, therefore according to rule number 3, EC times EA equals to EB times EM. Okay? EC times EA equals to EB times EM. So here EC equals to 10 minus X. EA equals to 10 units. And it is equal to EB. EB equals to 2 units times ME. ME equals to 6 plus 3 plus 3 plus 2. 6 plus 3 plus 3 is 12, and 12 plus 2 is 14. So in conclusion, EM equals to 14 units. In conclusion, we found out that according to rule number 3, 10 minus X times 10 equals to 2 times 14. 2 times 14 is 28, so I'll write it down. 28 equals to 10 times 10 minus X. Here we'll divide this equation by 10, and we get that 10 minus x equals to 28 over 10 is 2.8. Here we will add to this equation x, and we will subtract 2.8, and we will get that according to this equation x equals to 10 minus 2.8. 10 minus 2.8 is 7.2 units. So we actually found out that x, that is actually equals also to AC, equals to 7.2 units. Okay? So in both methods, we found out that the length of line segment x, that is also equals to AC, it is equals to 7.2 units. Okay, here x, that is equals to AC also, it is equal to 7.2 units. We finished with the second method. In the next step, I will summarize the lecture. Okay, we'll start with the first method. So I repeat on the question. We have here a semicircle that is inside the quarter circle. We know that side AO equals to 6 units. Side AC is tangent to the semicircle at this point D, and we want to find out the length of side AC, that is actually equals to x. So first of all, we define the center of the semicircle as point P, and the point of tendency of tangent AC with this semicircle as point D. And there, because of the fact that AOB is a quarter circle, point O must be the center of the quarter circle, and this angle AOB must be equal to 90 degrees. So here O is the center of the quarter circle. Point A is the point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, AO is the radius of the quarter circle, that is equal to 6 units. And OB is also the radius of the quarter circle for the same reason. It starts from the center of the quarter circle and ends at a point B, that is a point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, OB is the radius of the quarter circle, that is also equals to 6 units, of course. But OB, it is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter OB of the semicircle equals to 6 units. Therefore, the radius must be equal to half of it. That is to say, the radius of the semicircle will be equal to 6 over 2, that is 3 units. So OP, that is equal to PB, and that is also equal to PD. All those line segments are the radii of the semicircle, that is to say, they are equal to 3 units each. Why? Because they start from the center of the semicircle and ends at any point on the semicircle itself, and this is exactly the definition of a radius. That is to say, PB equals to OP equals to PD equals to 3 units. They are all the radii of the semicircle, that is equal to 3 units. Then we join points A and P together by a straight line. And then I presented to you rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So if we have this circle, and we have the first tangent to this We have the point P that is an external point of this circle, and from point P we draw two tangents to this circle. The first tangent is tangent PA. The second tangent is tangent PB. So here, according to rule number 1, the lengths of two tangents, that is to say, the length of the first tangent is PA, and the length of the second tangent is PB, from a common external point. Point P is a common external point to a circle. 2 points A and B are equal. That is to say, PA is equal to PB according to rule number 1. So whenever you draw two tangents to a circle from a common external point of that circle, then the length of those two tangents must be equal to each other. In this case, PA equals to PB. You can implement rule number 1 in our drawing, because in our drawing we have the common external point, point A. From this common external point, point A, we have two tangents to the semicircle. The first tangent is tangent AO, the second tangent is tangent AD. And according to rule number 1, the lengths of those two tangents are equal to each other. That is to say, AO is equal to AD according to rule number 1. But AU equals to 6 units according to what is given as the question. So can I tell that AU equals to 6, and from this equation 6 equals to AU equals to AD, we will derive that AD is also equals to 6 units. So here we can write down that AD equals to 6 units. Then we proved that those two right great triangles can go into each other according to side rule. So why those two triangles can go into each other? First of all, AO equals to AD equals to 6 units. Okay, AO equals to AD equals to 6 units. AP is a common side that belongs to both triangles. So AP equals to AP is a common side. And finally, OP equals to PD equals to 3 units. It is the radius of the semicircle. So we prove that all the sides of triangle APD can go into all the sides of triangle APO. Therefore, those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. That is to say, angle OAP equals to angle PAD. So if we define angle OAP as theta, here angle OAP equals to theta, then from this equation theta equals to angle OAP equals to angle PAD, we will derive that this angle PAD is also equal to theta. So both those two angles are equal to theta. Then we focus on the right triangle ADP. In this right triangle APD, we know that tangent theta equals to PO over AO. In the right triangle AOP, the right triangle, tangent theta equals to OP over AO. Here OP equals to 3 units, AO equals to 6 units according to what is given as the question. So tangent theta equals to 3 over 6. We divided both the numerator and the denominator of this side of the equation by 3. 3 over 3 is 1 and 6 over 3 is 2. So in conclusion, we found out that tangent theta equals to 1/2. Here tangent theta equals to 1/2. Then we join points O and C together by a straight line. So in this way we created triangle AOC. And we implemented the law of cosines in this triangle AOC. But before that, I presented to you the law of cosines that I have already showed the law of cosines in the previous lecture. So what is the law of cosines? The law of cosines is true in any triangle. If we have this triangle ABC, that could be any triangle. Side AB equals to A units, side AC equals to B units, side BC equals to C units, and the angle between side AB and side AC is alpha. Then, according to the law of cosines, C squared equals to A squared plus B squared, minus 2 times A times B times cosine alpha. Okay? And then we implemented the law of cosines in triangle AOC. In triangle AOC, this is triangle AOC that I copied from the original drawing. Angle OAC equals to theta plus theta, that is 2 theta. AO equals to 6 units according to what is given as the question. And AC is the line segment that we are looking for. That is to say, it is equal to x according to what is given as the question. So what is the length of OC? O is the center of the quarter circle. C is the point of the quarter circle itself, and this is exactly the definition of a radius. That is to say, OC is the radius of the quarter circle that is equal to 6 units. So OC equals to 6 units. Now we implemented the law of cosines in this triangle AOC. According to the law of cosines, OC square equals to AO square plus AC square minus 2 times AO times AC times cosine 2 theta. Okay? This is the implementation of the law of cosines in this triangle AOC. OC equals to x, so OC square is 6 squared, that is 36. AO is also equals to 6, so AO square is 6 squared, that is 36. AC equals to x, so AC square is x squared, that is AC square is x squared. Minus 2 times AO is 6 and AC is x, so it is minus 2 times 6 times x times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled. So in this side of the equation we have 0, that is equals to minus 2 times 6 is minus 12, so this expression equals to minus 12x times cosine 2 theta. Here we added 12x cosine 2 theta to this equation, equation number 1, and found out that according to equation number 1, x cosine 2 theta equals to x squared. We divided this equation number 1 by x, and we got here, in this side of the equation we have 12 cosine 2 theta, and here x squared over x is x. So in conclusion we found out that according to equation number 1, 12 times cosine 2 theta equals to x. So the only thing that is left to do in order to find out the value of x is to find out the value of cosine 2 theta. And we actually have trigonometric identity for cosine 2 theta. Cosine 2 theta, according to this trigonometric identity, equals to 1 minus tangent square theta over 1 plus tangent square theta. But we have already found out that tangent theta equals to 1/2, so we can substitute tangent theta in this trigonometric identity by 1/2. We did it, and we got that cosine 2 theta equals to 1 minus tangent square theta. If tangent theta equals to 1/2, then tangent square theta will be equal to 1/2 squared. So here tangent square theta equals to 1/2 squared over 1 plus tangent square theta is 1/2 squared. Okay, and 1/2 squared is 1/4. So this expression cosine 2 theta equals to 1 minus 1/4 over 1 plus 1/4. Okay, 1 minus 1/4 is 3/4, and 1 plus 1/4 is 5/4. So here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled, and we left only with cosine 2 theta, that is 3/5. So we found out that cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in equation number 1 by 3/5. According to equation number 1, 12 times cosine 2 theta equals to x. So cosine 12 times cosine 2 theta is 3/5, so it is 12 times 3/5, that is equal to x. 12 times 3 is 36 over 5, so x equals to 36 over 5, that is 7.2 units. So in conclusion, we found out that x, that is also equals to AC, This is equal to 7.2 units. We finished with the first method. Then I presented to you how to find out the length of line segment X according to the second method. Okay, here in the second method we use all the things that we have already found out in the first method. So here we know that this angle equals to 90 degrees. AO is the radius of the quarter circle, that is 6 units. OP equals to PB equals to PD equals to 3 units. It is the radius of the semicircle. We join points A and P together by a straight line. So those two triangles can correlate to each other according to side rule. We have already proved it in the first method. And from the fact that those two triangles can correlate to each other, we conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if this angle equals to theta, then this angle must be also equal to theta because they are equal to each other. All those things we have already done in the first method, and here from now on we continued with the second method. Here we did the construction. We extended line segment AC and line segment OB by a straight line until they intersect with each other. At this point, point E, point A is the intersection point of the extended line segment AC and the extended line segment OB. In this way, we created the right triangle AOE. In the right triangle AOE, AP, line segment AP, divides angle OAE into two halves. Each half equals to theta. And this is exactly the definition of angle bisector. That is to say, line segment AP is the angle bisector with triangle OAE. That is to say, we can implement the angle bisector theorem in this right triangle, triangle AOE. But first of all, I presented to you the angle bisector theorem, and only after that we implemented the angle bisector theorem in this triangle, the right triangle, triangle AOE. So what is the angle bisector theorem? So if we have this triangle, triangle ABC, that could be any triangle, and line segment AD divides angle BAC into two halves. Each half equals to theta, therefore AD is defined as angle bisector of triangle ABC. So according to angle bisector theorem, the angle bisector that in this specific triangle is AD. The angle bisector in a triangle related to this triangle, triangle ABC, divides the side that it eats. Angle bisector AD eats side BC and divides it into two parts. The first part is BD. The second part is DC, and the ratio between those two parts is BD over DC. So in a ratio that is equal to BD over DC, and that ratio is equal to the ratio between the angle's legs. We are relating to the angle that is being bisected into two halves, that is to say angle BAC, it is bisected by two halves. Each half equals to theta. The legs of angle BAC has two legs. The first leg is AB, the second leg is AC. And the ratio between those two legs is AB over AC. Okay? So the ratio between two legs is AB over AC, and that ratio equals to the ratio that angle bisector AD divides side BC. And that ratio equals to BD over DC. That is to say, those two ratios, they are equal to each other. In other words, AB over AC equals to BD over DC. Again, the ratio that angle bisector AD divides side BC is BD over DC, and that ratio equals to the ratio between the angles next, that is actually AB over AC, or in conclusion AB over AC equals to BD over DC. That is the angle sector theorem. Then we implemented the angle sector theorem in the right triangle, triangle AOE, ADE. It's actually the right triangle, triangle AOE. This letter is letter O. We implemented the angle sector theorem in the right triangle AOE. AO equals to 6 units according to what is given as the question. Here, OP is the radius of the semicircle, that is 3 units. And here, according to angle and AP is the angle bisector that divides angle OAE into 2 halves. Each half equals to theta. So according to angle bisector theorem, the angle bisector AP divides the side that it is, that is to say side OE, in a ratio that is equal to OP over PE. That is the ratio that angle bisector AP divides side OE, and that ratio equals to the ratio between the angles legs. We are related to angle OAE that is bisected into 2 halves. Angle OAE is 2 legs. The first leg is AO and the second leg is AE, and the ratio between those 2 legs is AO over AE. And that ratio equals to the ratio that angle bisector AP divides side OE. That ratio equals to OP over PE, that is to say those 2 ratios, they are equal to each other, that is to say OP over PE equals to AO over AE. Okay, here OP equals to 3 units, it is the radius of the semicircle, over PE equals to AO, AO equals to 6 units according to what is given as the question, over AE. Here we divided the question number 1 by 3 and we multiplied by AE, and we found out that 6 over 3 equals to AE over PE. 6 over 3 is 2, so we wrote it down that 2 equals to AE over PE. We multiplied this equation with equation number 1 by PE, and we found out that 2 times PE equals to AE. 2 times PE equals to AE, that is to say AE is twice as long as PE. We define PE as A, here PE equals to A according to our definition, and also here PE equals to A according to our definition. Now we can substitute PE by A in equation number 1. We did it and we got that A equals to 2 times PE. PE is A, so A equals to 2A. So conclusion, we found out that A equals to 2A, A equals to 2A, B equals to A. Now, in the next step, we actually, I copied again the right triangle AOE, this right triangle, and we implemented the Pythagoras theorem on this right triangle, triangle AOE. So this is the right triangle AOE. There's a copy from the original drawing. A equals to 2A. We already found out that A equals to 2A. AO equals to 6 units according to what is given as the question. And here, side OE equals to 3 plus A. Side OE equals to 3 plus A. So OE equals to 3 plus A. We implemented the Pythagoras theorem on this right triangle, triangle AOE. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AE squared equals to AO squared plus OE squared. AE is 2A, so A squared is 2A squared. And this is equal to AO squared. AO is 6, so AO squared is 6 squared, that is 36, plus OE squared. OE equals to 3 plus A, so OE squared is 3 plus A squared. So in conclusion, according to equation number 2, 2A squared equals to 36 plus 3 plus A squared. We open the brackets on both sides of this equation, equation number 2, and found out that 2A squared is 4A squared, that is equal to 36 and 3 plus a squared is 3 squared, that is 9, plus a squared plus 6a. Here 36 plus 9 is 45. So in conclusion, according to equation number 2, 4a squared equals to 45 plus a squared plus 6a. We subtracted a squared from this equation number 2, and found out that 4a squared minus a squared is 3a squared. A squared minus a squared is 0. So in conclusion, according to equation number 2, 3a squared equals to 45 plus 6a. Here we divided this equation number 2 by 3, and found out that a squared equals to 15. 3a squared over 3 is a squared, and 45 over 3 is 15. 6a over 3 is 2a. So in conclusion, I found out that a squared equals to 15 plus 2a. We subtracted 15 and also 2a from this equation number 2. And we found out that a squared minus 2a minus 15 equals to 0. So here we have a quadratic equation. The missing variable, the variable that we are looking for in this quadratic equation is a, so x equals to a. The coefficient a equals to 1, the coefficient b equals to minus 2, and the coefficient c equals to minus 15. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the variable that we are looking for is a, so x equals to a, and it is equals to minus b. B equals to minus 2, so minus b is minus 2, that is 2, plus 2, plus minus square root of b squared. B is minus 2, so b squared is minus 2 squared, that is 4. Minus 4 times a is 1, times c is minus 15. Over 2a. A is 1, so 2 times 1 is 2. So here we have a equals to 2 plus minus. Inside the root we have minus 4 times minus 15 is 60, and 60 plus 4 is 64. So inside the root what is left is only 64. So here a equals to 2 plus minus square root of 64 over 2. Square root of 64 is 8. So here we will have two solutions that are possible for a. A equals to 2 plus minus 8 over 2. And the first solution is a equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that a is a negative number that is equal to minus 3, but a is the length of side PE in triangle PE. So a as a length, it must be a positive number. It can never be equal to minus 3, that is a negative number. So we cancel this solution, and we left only with the solution, and a equals to 2 plus 8 over 10. 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that a equals to 5 units. So if a equals to 5 units, it means that 2a equals to 2 times 5, that is 10. So AE, that is equal to A equals to 10 units, and P equals to A, that is 5 units. Okay? Then we found out the length of line segment BE. From the drawing, it is very easy to see that BE equals to PE minus PB. B equals to PE minus PB. PE equals to A, that is 5 units. PB equals to 3 units, this is the radius of the semicircle, so in conclusion B equals to 3 minus 5, that is 2 units. So here B equals to 2 units, then we found out the length of line segment CE. For the domain, it is very easy to see that the length of line segment CE, it is equals to AE minus AC again, AE minus AC equals to CE. Here CE equals to AE minus AC. A equals to 10 units, AC equals to X. According to what is given as the question. That is the line segment that we are looking for. So, in conclusion, we found out that C equals to 10 minus X. Then I presented to you rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true, that PA times PB equals to PC times PD. So we have the external point P. This is the intersection point. Here chord AB intersects with chord CD at the external point P. Point P is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then according to rule number 3, here PA times PB will be equal to PC times PD. Again, PA times PB equals to PC times PD. We can implement rule number 3 in our drawing, because in our drawing we have chord AC that intersects with chord MB at point E. Again, chord AC intersects with chord MB at point E. Therefore, according to rule number 3, we get that EC times EA equals to EB times EM. Again, EC times EA equals to EB times EM. According to rule number 3, EC times EA equals to EB times EM. According to rule number 3, EC equals to 10 minus X, EA equals to 10, EB equals to 2, and EM, the long line segment EM equals to 6 plus 3 that is 12, and 12 plus 2 is 14. So in conclusion, EM equals to 14. So in conclusion, 10 minus X times 10 equals to 2 times 14. 2 times 14 is 28. So in conclusion, we found out that 10 times 10 minus X equals to 28. We divided this equation by 10 and we found out that 10 minus X equals to 28 over 10 is 2.8. Here we added to this equation X and we subtracted 2.8 and we found out that X equals to 10 minus 2.8. 10 minus 2.8 is 7.2 units. So we found out that X that is also equals to AC equals to 7.2 units. So I'll repeat again. Here AC that is also equals to S, to AC that is also equals to X, it is equals to 7.2 units. So in both methods we found out that the length of line segment AC that is equal to X, it is equal to 7.2 units. Okay, thank you very much.